sort of understand what's going on.
Yeah, why don't we start in on this homework, okay? Then we'll get to look at that test review. So yeah, homework is due Monday. It's these two here, and then those moment of inertia ones. We'll see if we get to those or not. So anyway, here's a wheel that rolls without slipping. Find the total acceleration of point A. All right, now again, this is that stuff where there's two ways to do it. You can do it geometrically or you can do it with a cross product. Whichever way suits you is fine. So what I would do on this is, so are there any questions on this, I guess, before we jump into that? Doesn't sound like there are. Okay, so good. Okay, so in this one, you got the velocity, you got the radius. Take the velocity divided by the radius, you get 3 radians per second. That's the angular speed. The tangential acceleration then is alpha times r. And you're given alpha, and you got r, so you can find the tangential acceleration at 0.8. Okay. The normal acceleration then is omega squared. You got omega at 3. You got r, so omega squared r, 3.6. And then as we were going over, whenever that was, I guess that was Friday, the tangential acceleration is also equal to the acceleration of the center of the wheel, the translational acceleration of the wheel, you might call it. That's alpha r also, so that's 0.8. So what we're doing here, we're finding the acceleration of point A, and to accomplish that, we just add all this stuff together. So what's going on is the whole wheel is accelerating at 0.8. That then is also the tangential acceleration. And then the normal acceleration goes from A towards O, and that's 3.6. So it's just a matter of looking at those 3 different accelerations as vectors and breaking them up into x and y components and adding them all up. And then if you can do that, you'll get this one, okay? So we got 50 degrees there, so I think that's also the angle here, 50, and that's a right angle, so that would leave 40 down below. All right, and then you just use those and just go ahead and go through and add everything up, okay, after you vectorize it. So the center of the wheel is going to the right, so that's an I component, 0.8 I plus 0j. Then you got the tangential acceleration going down left at 40 degrees. So minus 0.8 cosine 40i minus 0.8 sine 40j. And then the tangential acceleration is 3.6. And that's going from A towards the center of the circle, and that's a 50-degree angle. So that'd be minus 3.6 cosine 50A plus 3.6 sine 50j. Or minus 3.6 cosine 50i. I think I said A, it's I, plus 3.6 sine 50j. Okay. So you just take each of those, break it up into x and y components, and add everything up. You're going to add up the i's and the j's separately. And that'll get you the total acceleration of point A, the combined effect of those 3 things. So we doing all right with that? Do we got any questions on that? Okay, we're good. So you got those different things to add together. You just sum up the i's and the j's. There you go. So you're going to get negative 2.13i plus 2.24j. So if you want the magnitude, you take the square root of sum of the squares, and if you want the angle, you just do an arctan. I didn't put the sign in the arctan there, but it's 46.5 degrees with a negative x and a positive y, so that's up and left is what that is. So we good with that? Okay. So that's the geometric approach to getting that done. Okay. Now you can also do that vector style, and if you do it vector style, you're going to have a sub o at 0.8i, but then you're going to do a sub a with respect to o, which has the normal and tangential components. You'll go ahead and do that with a cross product and just a vector multiplication, okay? So you can also do this one in that fashion. So you get RA with respect to O to do this. So you've got the angle is 50 degrees, it's down right. So cosine 50.4i minus sine 50.4j. So that's 0.257i minus 0.306j. Okay, so you need that vector that's based on the angle there from O to A. All right, once you've got that, then what you would do would be to do a cross product between alpha. Now what you got there for alpha there is a clockwise 2. That's right there. So clockwise 2 is negative 2, and that's a k vector. So those rotational vectors are all k's. So that's 0, 0, minus 2. And then you cross that with RA with respect to O. And when you do that, you'll get negative 0.613I minus 0.514J. So that's the tangential. And then the normal acceleration, you square omega. There's a negative sign, and then you multiply it by R. So 3 squared is 9. Now the sign on the omega doesn't matter because you're going to square it. It's going to go away. But there's always that negative sign out front. Okay, that's part of the formula, so that stays. So that'll be negative 9 times 0.257i minus 0.306j, which is R there. And that'll get you A sub n. All right. And then once you've got that, you've got the 3 things you need. You got A sub O, you got the tangential acceleration of A with respect to O, and the normal acceleration of A with respect to O. So you just add them up, just like before, exact same thing that I was showing you there a minute ago. Okay. And that just looks like that. So that's the first one there. That one's fairly straightforward. If fairly straightforward there. So you just add up the 3 different things together. That's all you got to do. Okay. So we got any questions on that? Okay. So that's the first one. Now the second one might be a little bit more complicated. It's that linkage problem again. I give you alpha, and then you can use omega from your previous run at the linkage problem, okay? So the next one here, or actually, no, I'm sorry, this is a different linkage problem, but I give you omega for OA, and I also give it to you for AB, okay? So OA is 0.18, alpha is 0.07, and then I can't remember what omega AB is. Yeah, well, is it 0.45? 0.445, thanks. So it's 0.45. All right, so what you want to do there on this one is start from O to A and get the acceleration of A. A is alpha r. That's the tangential acceleration of A. So alpha is 0.07, r is the length of the linkage, 0.1, so that's 0.007 meters per second squared. So the tangential acceleration of A is going up that way, okay? And that's 0.007. And then the normal acceleration of A is omega squared r, 0.18 times 0.1, negative 0.00324, and that's going that way, in towards the center. Okay, so that's 0.00324 going in. So A sub A then is just the combination of those two things. Okay, so negative, excuse me, 0.00324I plus 0.007J. Okay, so that's how A is accelerating, because it's just rotating about O is what it's doing. So the next little bit on this is to go from A to B. All right. So that gets, we got a little bit more going on with that. The acceleration of A with respect to B, again, will be tangential and normal. We know omega, so we can find the normal, but we don't know alpha. So alpha will actually be an unknown as you're working through that. Okay. All right, so the tangential is alpha r, that's 0.08 alpha, because I don't know what alpha is yet. So what I do there is I assume that the tangential is going either upright or down left. I assumed upright, and so that's going to be 0.0693 times whatever alpha is, and that'll be the I, and then plus 0.04 alpha, and that's J. Okay, and that's the tangential acceleration. That's got two positive components because it's going upright. And then I'm going to have the normal acceleration, which is omega squared r, or 0.45 squared times the 0.08. That gets me 0.0162. Now that's going up left, so it's got a negative I and a positive j. So negative 0.0081I plus 0.014j. Okay. So that's what I get for those two relative components of acceleration. There we go. All right. So these rotational accelerations got normal and tangential components is what they've got. All right, now once you got all that stuff figured up, it's just a matter of putting everything together. You're going to do this relative acceleration equation. So the acceleration of B on that horizontal rod is A sub A, caused by the rotation of A about O, plus A sub B with respect to A, which we just calculated up. So everything I know, I just put into a big old vector equation there. So I've got the I's and the J's. So the I's I'm underlining here. I'm going to collect those, and I'm going to use that to solve for A sub B. To be able to do that, what I need is I need to use the J's to solve for alpha, okay? So I do the J's first, and I find alpha, it's negative 0.525. I just take that as is, plug it in to the I equation, and then I can go ahead and solve for A sub B. It's negative 0.0447 meters per second squared. We doing all right with that? Any questions? Okay. Okay. So that's that one. You could do it vector style too if you like. So if you do it vector style, again, the normal acceleration is negative omega squared times the position vector, r. And then the tangential is just alpha crossed with r. That's basically it. So you could do it either way. Remember, you got that cross product formula on your formula sheet. Okay? So whichever way suits is fine. So here I'm doing it with the vector approach. So what I want there is that position vector of A with respect to O. This is 0.1i plus 0j. Do a cross with alpha. Alpha is 0.07. It's counterclockwise, so that's a plus k vector. So those rotational vectors are k vectors when you're in two space. So I'll get 0i plus 0.007j. Then I can get the normal acceleration, negative omega squared r. Okay. And then add them up, and I'll get the same acceleration vector of A with respect to O that I had before. I'm just calculating the normal and tangential using vectors this time, that's all. Okay, it's just a different way of doing those calculations. Yeah, question there.
In the exam, do you want to see this cross products worked out by hand, or is it okay if we run those through the calculator?
Yeah, I'd like to see them. I'd like to see the work. The problem is not everybody can do those on a calculator, and it speeds some people up and not others. So yeah, I need to see some work on those. Okay. So yeah, the question was about showing work on the crosses, and yeah, I'd like to see them. Okay. Now, you know, don't overdo it. I mean, just show me what you're doing essentially, okay, so I can follow it. Okay. Okay, so that gets you down to A sub A with respect to O. And then you do the same thing to go from A to B. You just, you've got, you want the acceleration of B with respect to A. And again, that's a rotation. That's the important thing to understand about that stuff. And what you do then is a cross product for the tangential and just a negative times whatever omega is squared times the position vector. That'll get you the normal, okay? We're doing okay? Okay, so there you go. So what you need there, you need the position vector of B with respect to A. That's that notation. That's what that means. So that's 0.04i minus 0.0693j. That's just going from A to B. So that's this vector. And you're just using, of course, the 60-degree angle of the linkage to calculate that. Once you've got it, you take your unknown alpha and you cross it with the position vector. Okay. I've got that formula right on your formula sheet, or whatever way you do that is fine. And then also you find the normal acceleration by taking negative omega squared times whatever that position vector is. So you just factor a negative 0.45 squared times the position vector. And that'll get you the normal acceleration. Okay. Got any questions on that? We're doing okay? So that gets you the two components of acceleration, and then once you got them, you just plug them in. That's the same slide as I just showed you. It's the same dang thing. Okay, just get the total vector equation. The two unknowns are the acceleration of B and alpha. So I notice I've got an ABI here. So what that tells me is I'll use the J equation to solve for alpha. And then once I've got alpha, I'll use the I equation to solve for AB. That's how I go ahead and do that. Okay. All right. So we good on all that stuff? Okay. All right, why don't we have a look at this midterm review then? I think we'll do that next. We've still got those other 3 problems, but I think I'll come back to them later. Okay. Now this thing's online. See. Do you need a copy of this with you? Anybody else? First thing we got are the list of topics. Okay, so work and energy is first. So when I see problems that involve force and distance, and height, velocity, and springs, I start thinking about work energy. Okay, so you do want to think about which method goes with which type of problem. Okay, so the potential energy is the weight times the height. You call out your own datum wherever you want it to be. It's fine, but just once you establish it, stick with it throughout the whole problem. You can't be moving it around in the middle of a problem. Okay. Spring energy is 1/2 ks squared. There's also a formula there for spring force. Remember to use the one for energy, 1/2 ks squared. S is the stretch or compression in the spring, not the length, but the amount of stretch or compression. And kinetic energy is 1/2 mv squared. Okay. Then we have work that comes from outside the system. That's the force times the displacement. In our problems, work is usually some type of friction. Okay. Or air resistance or something like that. Okay, something from outside the system that's affecting it. Positive means energy added to the system and things speed up and go higher and you have, whatever, more spring compression and that sort of thing. Negative means energy is removed from the system, which makes things slow down or lose height or things like that, okay? Remember to multiply the force times the distance. That's how you get energy. Okay. You can also look at power, which is work over time. It's the amount of work you can do in a given amount of time. And then efficiency is whatever you put out versus what went in, either energy or power. Okay. So that's the work energy stuff. Okay. Impulse momentum, we got force and time, moment in time, collisions, 2 or more objects interacting. Certainly if you got collisions or 2 or more objects interacting, you got to use momentum. Okay. And you got that momentum impulse equation. The units all work out on that, but stay in standard units. Get everything into newtons, meters, kilograms, or pound, feet, and slugs. Okay, now energy is not a vector. Energy is an amount of energy. It's a magnitude. Okay. But momentum is a vector. So remember that, okay? That momentum is a vector. You've got to treat it that way. We also went through the coefficient of restitution, which is that E value. There's a formula for that. And then angular momentum, where we add moment arms to the terms of the linear momentum problem, and they change a little bit. So we get dmv. D is the offset distance, like a moment arm. V is the linear velocity in meters per second or feet per second. Okay. The FDT becomes MDT. The M is moment there. Okay, so that's moment right there. As opposed to this lowercase m, which is mass. So keep those straight. Okay. If we have more than one object interacting, we've got some sort of collision or interaction between 2 moments, two objects, we can often omit the impulse because the force of one object on the other is the exact negative of the force of the second object on the first. Okay. All right. All right, with that. Rotation, we just actually went through a little bit of that. You can do it vector or geometric, either way. We've also got these relationships up above that describe constant and instantaneous types of alphas, okay? So if you've got alpha as a function that changes, use the top value, top equations. If alpha is constant, use the ones below. Okay.
Did you say that, that acceleration stuff will not be on the test?
I said the relative acceleration stuff won't be. What we just went over for the homework will not be. But alpha could be. Yeah. Okay. Okay, then we did wheels that rotate without slipping. The velocity of the tangential velocity equals the velocity of the wheel as a whole. Okay. Relative velocity, we just went through relative acceleration. I'll point out a couple of things about that in a minute. Instantaneous center of zero velocity, these are pretty much interchangeable as far as when you use them. I won't spec a method, you can do it. Do problems whatever way you wish. I won't tell you what method to use. Okay, relative acceleration we won't have on the test. Okay, that's the stuff that will not be on there. Okay. All right. All right. Okay, now there's a linkage problem. You'll probably get something like that on there. And like I say, just that's a practice problem if you need it. We did one in class. We had a couple homework problems. Just be able to knock through one of those, figure out what method works for you here, and just be able to apply it, okay? Now, common errors to watch out for. If you're doing vectors, so for example, if you're looking at linkage AB, okay, if you're doing it vector style, you use 56 degrees. Okay, because what you're doing there, if you're doing it vector style, is you use linkage AB is what you're using there. It's RAB is what it is, okay? So the angle is 56 degrees. If you're doing it geometric style, you use VAB, okay? And if that's the case, you don't want to use 56 degrees. You want to use 90 minus 56. Is that 34? Because what you're doing there, you're using the velocity of actually B with respect to A. So why don't I get my notation right here? These would be B with respect to A. And so you'd use 34 degrees, okay? That's a distinction that people sometimes seem to miss. So the angle you use depends on the method you're employing, okay? You all good with that? Okay, now the other thing with geometric, for VBA, you can assume minus, plus, and plus, minus. You could assume either one of those for VB with respect to A, okay? But you can't assume plus, plus, and negative, negative. That just won't work because the velocity of B with respect to A can't be those other two things. It can't be plus, plus, because if it's plus, plus, it's doing that. It ain't doing that, okay? It can't, because it's rotating about A. Nor can it be minus, minus, because that would be shown as like that, and it's not doing that, okay? So keep that straight, your signs, if you're going to do it geometrically. So if you're doing it geometrically, use 90 minus the linkage angle, and keep your signs straight. Look at it, draw a picture of it, go with one side or the other, and use those signs, okay? You can't just arbitrarily throw signs in there. Sometimes it doesn't work. If you're doing it vector style, use the linkage angle. Okay? You all okay with that? Those are just, I'm just saying that because those are common errors I've seen in the past that I just want you to avoid. All right. All right. And I don't know as I'll do that one. I think it's better if you do it, really. I mean, it's okay. But are there any questions on that one? I mean, if you haven't done it already, I'll do it just to practice on your own. You got those intermediate answers. Okay. All right. Okay, this next one's a work energy problem. What you want to do, you want to see how high this thing will be shot up the ramp. Now, the tricky little thing on this, or it's, I don't know how horribly tricky it is, but it is something you have to consider, is you want to get the height, is what you want. But you also have the distance up the ramp, the angled distance up the ramp is an unknown. So what you got to do is relate those things together. Okay, so here's how you do that. The distance up the ramp, which I'm calling D, is times the sine of 32 is the height. So instead of the height, I can use 0.5299D, and instead of D, I can use 1.887H. So, because if you don't recognize that, you're going to have two unknowns in there, too many, but H and D relate to each other, okay? So you want to pick that up on that one, okay? You want to get the weight of the block, not the mass. It's 14.72, at least for the potential energy anyway. And then you want to go through the rigmarole here and get in the friction. Use the cosine of the ramp angle to get the normal, 12.48. Multiply that by the coefficient of friction, 0.22, so it's 2.75. Then multiply that by the distance, 1.887H. Okay. So remember to multiply that frictional force by the distance. Remember to use cosine of the ramp angle for that normal force. Okay. Everybody good with that? Also get the stretch or compression in the spring. So I've got that there. So SA is 0.53, which is the unstretched length, minus 0.23. So there's 0.3 compression in there. And then after the thing is shot, there's still compression in the spring you have to account for. So 0.53 is actually the uncompressed length. And that's 0.37 is the final length. It's 0.16. There we go. Okay. So we got everything ready to go here, and we just plug it into that table. Potential energy is 0 to start at A. The spring energy is 1/2 Ks squared. Okay. It's 18.45. That'll be the total energy at A. The work is friction times distance. Distance is expressed as a function of H. So that's 18.45 minus 5.18H. The potential energy is the weight times the unknown height. And the spring energy, again, there's still some energy left in the spring, so we want to account for that at B, 5.248. So we know the total remaining energy, the initial energy minus the work, is equal to the spring energy plus the potential. Okay. So we just equate them, solve for H. That's how you finish this thing up. Okay. Any questions on that? Doing all right? We're good? And what is, I can't remember what H comes out to be. You know, it's just a matter of solving for it. So you just equate this stuff to that. So, 18.45 minus 5.18H is equal to 14.72H plus 5.248. Okay. So there you go. And you just solve for h. Okay. Good. Okay, the next one there, that's a momentum problem because you got two objects that are knocking into each other there. So you've got to treat that thing like a vector. So we got that initial momentum, mass times velocity in the x direction. So that's all I there. It's 0.96 I and 0j, because the only thing that's moving is that all a in the x direction. And then you've got all the stuff that happens afterwards. So we got 11-degree angle, but that's with the y-axis. So 0.7 times sine 11 times 0.42 will get you the x component of momentum. Okay. And then 0.7 cosine 11 times 0.42 will get you the y component of momentum. That's for ball B. For A, I don't know what they are. So I got 0.8 Vx and 0.8 Vy. Notice I'm not doing any trig in there. I don't need to get the angle yet. I'm just going to find what the x and y components are. So I'm not messing with any trigonometry in there. So I get the stuff on the left, and I got the stuff on the right. And I've got two unknowns, Vax2 and Vay2. So those are the x and the y components there that are unknown. And they're both times 0.8, which is the mass of A. And then I've got the components of momentum for B, which was found using trig. Pull out the x's and solve for that, it's 1.13. Pull out the y's and solve for that, it's negative 0.361. That's the x and y components of the velocity of A. You can find take the square root of some of the squares and get the velocity of A, and you can also find its angle. Okay. We're doing all right with that? Okay. So that's a pretty straight up momentum problem there, just based on vectors. Just using trigonometry to break it up into x's and y's. So again, remember that work energy is a magnitude, momentum is a vector. Okay. Okay. Good with that. So there's the final bit on that, just taking the square root of some of the squares to get the velocity of A. All right, okay, this angular momentum thing here, we've got okay, we're on a flat table. That means the horizontal plane. Okay. So these are always older problems. Nowadays, I probably would use this term in there for this one, meaning it's acting, on a flat table. It's not up and down. It's on the horizontal plane. I would contrast that with the vertical plane. Vertical plane, I'll put an arrow in there somewhere, okay? And the up arrow, horizontal plane, of course I don't. Okay, so this one, nowadays, when I do this, I'd put an arrow in there and say up, so you're real clear how that's going, because I've had confusion on that in the past, and it just blows up the solution process if you don't recognize that. So up means like that. Okay, this here I would use the term, I'm using the term pool table and stuff like that. Obviously that's horizontal plane, but this is the kind of the key word, for what I mean by that. Horizontal plane, quite often if it's happening on a table, I might have that word too, okay, flat, good, okay. it affects friction and potential energy and all that stuff. So it's really important to clarify that and be sure you know which way we're going on that, okay? All right, so this one's on in the horizontal plane. What you're going to do, you're going to recognize that things are rotating. We've got like a hole in the table and we're letting cable out of the hole as the thing rotates. So this one's pretty straight up. Now all the force is pulling in towards the center about which it's rotating. So this will zero out here. So you're just going to take that initial distance, the 0.8 meters, multiply it by the mass, which is 1.6 kilograms, and then the velocity. And I don't know, the one thing that has come up over the years on this is because it's angular momentum, people get confused on what type of velocity it is. The key to that is just to look at the letter. It's v. So that is a linear velocity, 1.2 meters per second. And then you'll equate that to 1.1 meters, 1.6 kilograms, and the unknown velocity there. And just work through the calculations there, and you can find what the velocity is. Let's hope it's 0.873, but we'll find out. Yep, 0.873, okay? So that's all that's going on with that. Got any questions on that? Good. Got a little fancier one here, just a motor rotating, throwing a mass to the outside as it rotates like it would. We've got a motor introduces 48 Newton meters, so your impulse would be that moment. That would be an angular impulse times the time over which it acts. The initial angular momentum is 0.42, that's d. We got m, and then we've got r, what we were calling at that time theta dot. We could also call it omega. So r theta dot are equal to v. Okay, you okay with that? So r and d are the same number on this, okay? So then you got the moment, you got the time, and what do we got over here? We've got d, m, and then actually I used omega this time, so why don't I change that so it's omega. Omega and theta dot are the same thing. Okay, and that's r omega. Okay, so that's how that one's set up. So, you know, watch these rotational ones. It can be angular momentum, okay? Once you get the basic concepts there, you know, they're pretty straight up to, you just plug into that formula. You just gotta have to know what to plug in where, I guess. It's a positive sign on the impulse because that motor is gonna make that thing go faster. Okay. Any questions on that one? You doing all right? Okay. You got any other general kind of questions about this thing on Thursday? Doing all right?
Any questions you might suggest from the homework?
Oh, I can't think any to pick out. You know, just be darn sure you know how to do that relative velocity stuff, or, you know, however you like to do it. Just improve it to yourself. You got that example I gave you here. Do it yourself. Make sure you can do it. If you got questions, ask me tomorrow on that. I don't know. And, you know, just remember, I've kind of pointed out some of those things. Those are common errors. So all that stuff I kind of went through, the angles and the signs on the relative velocity and the fact, you know, the work energy stuff that I pointed out. It's a magnitude momentum's a vector, and just that kind of stuff that I kind of tried to call out. That's about it. I mean, I can't think of anything particular to pick out. Okay. All right. All right. We good to go then? We doing all right? Okay. All right. Well, hope your physics test either went well or goes well.